Hi, my name isn't me, 3Bagain. I'm from BSED Math 3B, and in partial fulfillment of the M115 abstract algebra, I am here to present my geometric model. Okay, so geometric model M115 abstract algebra. So the title of my geometric model is Crystal Symmetry. My model is based on snowflakes. I use this because it reminds me of my lifelong dream of feeling and having an opportunity to see snow or snowflakes in real life. And I trust that I will in God's perfect time and guidance. Okay, so let's move forward with these labels that I use for this model. So the letters I, L, Y, S, O, M, E, D are for front moves, or the labels or the elements that I use for front moves. The numbers 1, 4, 3, 6, 2, 5, 7, 8, on the other hand, are for back moves, or the elements that I used for the back moves. Each letter or number represents a rotation transformation on the snowflakes. And this one, as you can see, I defined the back twice. As it is, meaning how it is if you look at the back without rotating it, and after we rotate it, back after rotating. It shows the number at the back. So it will show that 1, 4, 3, 6, 2, 5, 7, 8, and ILYSOMED. And then let's check. This is the crystal symmetry, and this shows that they are the same, or ILY is isomorphic, or the same with I at the back, or the elements at the back, and L is isomorphic to 4, Y is isomorphic to 3, S is isomorphic to 6, O is isomorphic to 2, M is isomorphic to 5, is isomorphic to 7, and D lastly is isomorphic to 8. Now that we know that this would be, or counting the elements in the front, we will have 8 elements, and counting at the elements at the back, we will have another 8 elements for a total of 16 elements, or 16 moves. So 8 and 8 is equal to 16 moves. So looking at the snowflakes, we will see each labeled element, which is ILYSOMED and 1, 4, 3, 6, 2, 5, 7, 8, which is the group of H. Now, let us discuss the following moves, starting with the front moves. I is equal to do nothing. L is equal to 1 turn to the left. Y is equal to 2 turns to the left. S is equal to 3 turns to the left. O is equal to 4 turns to the left, and 5 is equal to 5 turns to the left, and 6 is equal to 6 turns to the left, and D is equal to 7 turns to the left. Okay, and that would be the what do you call this one? The moves for the front moves. Let's check for the moves of back after rotating, or the back moves. We have 1, which is rotate to the right. So looking at the front, or looking at the ILSOIMD, you rotate to the right, and it will reveal the 1, or the moves of back. And then 4, the same, you will need to rotate it or flip it, and then turn to the right for 4. And then the same with 3, you need to flip it to the right or rotate it to the right, then 2 turns to the right. And then we have the 6, you need to rotate to the right, and then 3, which is 1, 2, 3, which is 6. 3 turns to the right. And then for the 4, for the 2, we need to turn it to the left. So 1, 2, 3, 4, it would be 2. And then for 5, it would be 3 turns to the left, which is 1, 2, 3. And then 7 is 2 turns, 1, 2. And then 8 would be the last one, or 1 turn to the left, which is 8. So those are the moves for the back. Okay, now all the possible moves we have ILSOMD, which is one turn to the left, two, three, four, five, six, seven turns to the left, and then the all the possible moves for the back would be 1, 4, 3, 6, 2, 5, 7, 8. Flip to the right or rotate to the right, then one turn to the right up until six, and then when we reach the six, two would be four turns to the left, and then up to eight. Now that we are all familiar with the labels or the elements that I've used in my geometric model, we will now be discussing how this or how each element work. With the first one, I star I. If we are talking about I star I, it means that I times do nothing, right? So if you times do nothing to do nothing, it will still be nothing, or do nothing, it will still be the same, which means it would still be I. The same with everything with ILYSOMED 1436257 8, and this one, everything that you manipulate or you multiply or use used for I, it will still be the same with the multiplier or this number. So everything in this one would be the same with all of these part or the header. Now we will see this one, this one. Now let's move forward with the L star L, which is this one and this one. That is our next, that is the next part that we will be applying this one. So let's see the answer. If we use L star L, which is one turn to the left and then one turn to the left, what would be the answer? If the L, you are already looking at the L, and then you turn it one to the left, which is, it would be Y. So let's check if it would still really be Y. And it really is Y. And now let's check the next one. We have the L star Y. So you're already looking at the L, and then we will do the move for Y, which is two turns to the left. And what would be the answer? Let's check. S. The same with the L star S. We're already looking at the L, which is at this one, and then we will do the move for S, which is three turns to the left. This one, three turns to the left. So from L, 1, 2, 3, it would be O. Let's check if it would be O. And it is really O. So the same with L star O. We are already looking at L, and then we will be doing the move for O, which is four turns to the left. 1, 2, 3, 4, it would be M. Let's check. And it's still the same. It will be the same for everything. So it would be E, and then D. For L star E, it would be D. And then for L star D, it would be I, which is it will be doing the 360-degree turn. Okay, now that we are already familiar with that, let's move forward with L star 1. L star 1. If you're already looking at L, which is the one turn to the left, we're already looking here. We will be doing the move for 1. What is the move for 1? It would be rotate to the right. So looking at the L, so we're looking here, and then if we twist it, what is the number at the back of L? Let's see. It would be, okay, let's check what would be the L star 1, which is rotate to the right or flip. We have 4. Okay, so that would be the answer. So the number at the back of L would be 4. So next, let's check. We're still looking at L. But now we need to do the move for 4, right? This one, we're doing the L star 4. So what is the move for 4? We have rotate to the right, then 1 turn to the right. So after rotating, which is this one, we need to rotate it to the right. So to this part would be this, to the right, which is clockwise. Okay, so the answer would be, let's check, 3. Okay, because we rotated it to the right. So the same with L3. What is the move for 3? We have rotate to the right, then 2 turns to the right. Okay, so we're doing 2 turns now. Let's check what would be the answer. It would be 6. Okay, so that would be, what do you call this one? 2 turns to the right. So 1, 2, just this one. 6. So now we have number 6. What would be the move for number 6? We have rotate to the right, then 3 turns to the right. So looking at the 4, 1, 2, 3, 4. So it would be 2. Let's check if it's 2. Okay, L star 6 would be 2. Okay, next, L star 2. Let's check what is the move for 2. We have rotate to the right, then 4 turns to the left. What would be the answer? Let's check. It's 5. The same with 5. We will be rotating it to the right and then 3 turns to the left. So now we will be doing the counterclockwise already because we're moving to the left. So this, we are already moving to this side. Okay, or we will be rotating to this side. Let's check what will be the answer. If we do the L star 5, we have 7. Okay, so 4 be 3 turns, 1, 2, and then 3. Perfect. We have the number 7, L star 7. Rotate to the right, then 2 turns to the left. So looking at the 4 we have, it would be 8. Would it be 8? Let's check if it's 8. And it is really 8. And the last one, we have L star 8, which is L star 8. It means 1 turn to the left only. So if we turn to the left, we will be going back to 1. Okay, which is this one. We already went back to the I. This one. I mean 1. Okay, so that would be everything or the movement for L. So if we keep on doing that for Y and so on and so forth, we will be having this table of result. Let's check what will be the table of result. So now, looking at the completed table, which is this, after doing all of the elements per element, so we did the, what do you call this one, L star to everything here. And then we did dy to everything, and then s to everything, and then o to all of these 16 elements, then m to everything. And then we have here, as we have here, the completed table using our 16 symmetries and model. All we need to know now if this forms a group structure. Okay, so we will be checking as we go on if this model that I've chosen, which is the crystal symmetry, will be forming a group structure. So let's see. By looking at the next page, we have here the table of result. And now let's move forward with this one. A mathematical group structure is defined as a set with an operation that satisfies 5 properties. So what would be those 5 properties? We have the number 1, it should be well defined. It should be close, or it should has a closure, and it should be associative or has associativity, it has identity, and it has an inverse for all. Okay, so those would be defined as a mathematical group. So this table defines a closed binary operation, as we can see, because there is, or everything here, all of the elements, all of the values that we can see inside this table is already or can be seen at the given set that we have, which is the 16 elements or the set of group H. So all of this is closed because it is within the given set. So now that we know that it is closed, let's check the others. Now let's check if it's well defined. Okay, if it's well defined, it shows that this table is well defined. Well defined means it is unique or it has a unique output for each input pair, meaning the table shows exactly one resulting element for every combination of two elements. Example, we have L star Y is equal to S and O star M is equal to L. And let's check the Y star L is equal to S, and then L star Y still is equal to S. It means these two, or L star Y, is the same combination of Y star L. But if we did O star M, it is equal to L. So all of these, or the combination of two different numbers, would be, or it would give you two possible outcome or one possible outcome. So there are no cases where A star B or any of this combination of two gives two possible outcomes. Okay, so that it means it is well defined. So I already discussed that this is close, but let's check how it is close. So okay, so this one, it is well defined. The table shows exactly one resulting element for every combination of two elements. There are no cases where A star B gives two possible outcomes, therefore it is well defined. And now we will be looking if it's close. Is it close? So all combinations of elements remain within the set, which is what I've discussed earlier. Every operation result is still within the original set, which is the group H, ILYSOM, ED1436257. Therefore, it is close. And now let's check the others if it's associative. Is it associative? Okay, that would be the question. To check if it is associative, we will rotate the table to 180 degrees to see if it is symmetrical to our original table. Okay, so after rotating, let's see what would it look like. And also, we all know that associativity means that for any three elements, A, B, C, the equation A star B star C is equal to A star B star C holds. So to check if it will still be the same. Okay. Okay, this one. I rotated the table 180 degrees to see if it is symmetrical to our original table. Then I interchanged rows to verify the structure of the table. Okay, so we will be looking at the next slide after showing you. This would be the 180 degrees. And let's see how it looks like if we flip the numbers inside. So it looks like this. So after this one, it would look like this. Okay, so after making the table what do you call this one? Looking at, we rotated the letters inside the table so that it would be normal for our eyes. We have here the same with this one and this one, but we will be looking here and this one if it's the same with this one and this one. So as we can see that the top part or this part is the same, this one is the same with this one, but the next one or the vertical side or the vertical part of these tables are not aligned or not the same. So we will be interchanging some row. We will be starting at the D row, switches place with the L row, which is the brown one, we can see. So we will put this one here, and then the L would be here at the D. Okay, and then let's check what would be the next or the other letters that we will need to switch, and then E rows, which is placed with Y row, which is the yellow one. We will be switching the Y to E so that it will be ILY. And then what will be the next? Let's check. We have the row of M. Okay, we have here the row M switches with S row, which is the green one. So ILYS should it be? It should be S here, not M. And then let's check what would be the next one to make everything correct. We have this one, the 7 and 1. So the 1 should be at the top here. It should be here, not there. Okay, so now that we have the perfect structure for these, we have ILYSOMED, and then we will be arranging the number part or the back part so that it will be the same with our original table. So we'll be interchanging 7 rows, which is placed with 1 row, which is the red one. And then we will be switching the 4 and 5, which is the violet part, which is this one. So it should be 1, 4, and not 1, 5. Let's check what will be the next. It should be 3 and 2. 3 and 2, which is the gray part, we will be interchanging them so that it will be the same with 1, 4, 3, and then 6, 2, 5, 7, and 8. Okay, let's check. And okay, wait, it didn't. What happened? Okay, so I think that would be it. And then the next part would be this one. As we can see, it's already color. Okay, wait, let me just. Okay, again. So after interchanging some rows, especially the gray one, which is the 1, 4, 3, 6, 2, 5, 7, 8, we have already reached the same, which is ILSOMED 1, 4, 3, 6, 2, 5, 7, 8. So let's check what would be the look of the interchanged rows or the result of interchanged. We have this one, ILSOMD, ILYSOMD, LYSOMED, and the same with the original table as we can see, right? The same, this one, and then ILYSOMED to 8, it's the same, 7, 5, 2, 6, 4, 1, D 1, 4, 3, 6, 2, 5, 7, and 8. and it's the same. So now that we know that the result of interchange is the same, it is associative. So it is indeed associative. The operation table remained, as we can see, remained consistent, meaning they are indeed symmetric. Therefore, there exists an associativity in the table. Okay, so now that we know that it is well defined, close, and associative, let's check if it has an identity element. Does it have an identity element? Let's check with this one. Does identity element exist? The identity I, okay, the identity I, this one, when any move is combined with I, the result is the move itself. Therefore, it has an identity element. So we know that this one is the identity element because everything that you multiply or you combined with this I move, which is do nothing, the result will be the number that you multiplied with, which is this one. Therefore, it has an identity element. So now let's check if it has an identity, I mean, if it has an inverse element for all. Does an inverse element for all exist? Okay, that would be the question. Let's check. So as we can see here, I prime is equal to I, and then L inverse, L prime is equal to D, Y prime or L, I Y inverse equal to E, S inverse equal to M, O inverse equal to O, M inverse equal to S, E inverse equal to Y, D inverse equal to L, 1 inverse equal to 1, 4 inverse equal to 4, 3 inverse equal to 3, 6 inverse equal to 3, 2 inverse equal to 2, 5 inverse equal to 5, 7 inverse equal to 7, and 8 inverse equal to 8. As we can see here, it's this one. L, where's the I in L? It's on the T, as we can see. That's why the inverse of L is T. And then Y, let's check. It's in the E, as we can see. That is why the inverse of Y is E. The same with S. If we look here, we can see it in the M, the I, and then that's why the inverse of S is M. And O, if we will be looking at O, the intersection of I would be at O as well. That's why the O is the inverse of O. And the same with M, E, and D. And then at 1 inverse, we have here the I. So if we will be looking, the intersection of it would be at 1 as well. And then let's check at 4. It would be at 4 as well. 4 and 4. The same with 3, 6, 2, 5, 7, and 8. So it means the number part, the inverse would be themselves also. Okay? Because we can see the I here, all of this, the I is at the intersection of the same number as well. So now we know that it has an inverse for all. So does an inverse for all exist? Since an identity element exists for every row or column, as we can see, it is I, therefore it has an inverse for all. So I think that would be it. We now know that this table or this whole table or my group H is equal to the I, L, Y, I, L, Y, S, O, M, E, T, 1, 4, 3, 6, 2, 5, 7, and 8. The group H, therefore, the geometric table snowflake, which is or has a 16 symmetries or elements forms a group structure because it forms a group structure because the following conditions are satisfied. What will be all the conditions? It is well defined. It is close. It has or it is associative. It has an identity element and it has an inverse element for all. Therefore, crystal symmetry or the group of H, which ILSOMED 1436257 or my 16 symmetry geometric model forms a group structure. So again, my name is 3Bagain, and this is my project number 1. Thank you so much for listening and have a great day. Thank you.